So let's start with the review with slope fields. It's and finding approximate solutions. Consider the following slope field. That's the graph, and it's asking us to match one of the following differential equations to the given slope field. As I'm looking at the differential equations, only one of them is not autonomous. So with non-autonomous, basically differential equations, you may actually expect the slope field to change on any horizontal line, basically. Let's pick this line. And so what is that point? That point is 0 and 1. If I test it in here, y prime is going to be 0 times sine of pi half and minus 1, which is going to be minus 1. And then if I move a little further, let's say at 1 and 1, again on the horizontal line, if I plug in, I get y prime is equal to 1 times sine of pi half minus 1, which is 0. In this case, you see that here it should have been, if this was the function, here we should have had a negative slope and then 0. And then again, if you try something else, let's say um, um, 2 and 1, you will get you get another value, basically. I think you get plus 1. And so the slope should have been changing. So this is not it. This is out. It remains between these two. One thing that I say is try the equilibrium solutions. In both of these cases, the equilibrium solutions are solutions um, to the equation sine squared pi y over 2 equal to 1. And that is sine of pi y divided by 2 equal to plus minus 1. And if you solve, y has to be an odd number, basically. And it actually, all the equilibrium solutions are there. There are, for odd numbers, you can see them. The next thing, I just said that one is negative of the other in here. So best thing is to have a test point. Let's see, any test point would work, but let's try, for example, 0, 0. And I'm trying 0 and 0 for both of these to see what I get. And for the first one, I get y prime is equal to negative 1. For the second one, I get y prime is equal to 1. And at 0, 0, the direction is positive, so this is the answer, and we circle it around. The next thing is using the slope field, sketch the approximate solution curves passing through the initial points 0, 0, 0 0.5, 0, negative 0.5, 0, negative 2. So here, let's start. One of them is 0, 0, the other one is 0 0.5, 0. So 0 0.5, 0, 0, 0, and negative 0.5. And the last one is 0, negative 2. 0, negative 2. And then I can see that the solutions are kind of going upward, and they should go and converge to the equilibrium. And down here, they go that way. A little smoother than what I drew. And then over here also, and over here also. They're all converging. As t goes to infinity, they converge to y equal to 1. In fact, it's very obvious. Y equal to 1 is stable equilibrium from below. It is not stable from above, so it's not fully stable, it's semi-stable. And then from 0 and -2, I see I go this way, and down there I go that way. Again, in this case, the values converge to y equal to -1. Again, this equilibrium is semi-stable, stable only from below. Knowing all this information, I go back here and I say limit of the solution y, or y of t, however you want to name it, is going to be 1 as t goes to infinity when initial point are 0, 0, 0.5 and 0 and -0.5. Then we saw in the picture limit of y of t is equal to -1 as t goes to positive infinity when initial point is 0 and -2.